check is. So we've got something that looks like that, right? And this is b to the power x or n. And then, I don't know if you remember your terminologies, but this here, all of this is called a power. This here alone, the alphabet, the letter B alone is the base. And this here is the exponent or index. All right. And an exponent indicates the number of times a certain number or base is multiplied by itself. This is how many times base is multiplied by itself. How many times base is multiplied by itself. So in other words, if you have negative 2 to the power 3, that's the same as negative 2 times negative 2 times negative 2, which will give you negative 8. So this explains that. All right. So it's how many times the multiplication is repeated. So and or how many times the multiplication is repeated. Yeah, so if we have 1 over 5/12, that's the same as 1 over 2 to the power 9.
So you have to make that example. That's funny.
But it's the experience that got me to guess it correctly. What's wrong with that?
It's fine.
It's fine. Alright.
What is it lagging?
I have no idea. But maybe I'll try and refresh it. Let's see.
And you're on the second page.
No, on the second page. Just put this in a bubble. Put it in a bubble. Put this also in a bubble. Put it in a bubble, in a bubble, in a bubble. In a bubble. Alright. So now, the exponential function, f of x equals a base to the power x. We've got 3 conditions for the graph, right? In the first case, where b is greater than 1. And then we have a second case where b is less than 1 but greater than 0. And we also have another thing to consider where b is less than or equal to 0. Oh yeah, and also the reason why b cannot be equal to 0 is because if you take any number, or rather if you take 0 and you raise it to any number, the answer will still be 0. So for the first case, why is the screen not refreshing? as fast.
We're on page 2.
Also, let's do page 2 here. Okay. Can I show you how to do the controls? So you also see what's happening here. I mean, you can also flip through what's happening here.
Yes, I can just press the arrow.
Yes. Okay. You'll do that for us? Okay, cool. So for the first instance, our graph looks like this. It intercepts at +1 and rises exponentially like that for values of x that are positive. And for values of x that are negative, the curve is asymptotic to to y equals 0. No, wait, what? The x-axis is an asymptote for x values that are negative. Yes, that's what I want to say. So this would be y equals bx for b that's positive. And then for this graph, it intercepts at y equals 1 as well. And this is positive x, positive y. And this is for b that is less than 1 or greater than 0. So on your values of x that are negative, your graph increases exponentially. But for values of x that are positive, then the x-axis becomes an asymptote to the curve. I just want to put this one in a different color. Then I'll do different color. One equal different color.
But this means we're gonna have to refresh this every single time you write.
The screen.
Yeah.
Yeah, it looks like it. Because it seems I'm writing a bit faster on the handheld device. But it also looks cool when it comes after. Alright, so this is y equals b to the power x for b is less than 1, greater than 0. And we don't have the graph defined for b is less than or equal to 0.
Okay.
What did I just do? Alright.
Investigation.
So now we're going to investigate the inverse. So inverse exponential functions. Interesting. Inverse exponential functions. If we have a function y equals x over 3 plus 10, and we have another one that's y equals x squared over 3, then we have another one that equals 10 to the x, and another one that equals 1 over 3 to power x. Let me just y equals 3 plus 10. Alright, so we're gonna have type,
Type of function.
yes, and then inverse 1 and inverse 2. Alright, so what kind of function is the first function? Y equals x over 3 plus 10. What type of function is it? Is it a linear? Is it a quadratic? Is it an exponential? Is it a
I want to believe it's a linear.
linear? Why do you sound like you doubt it?
Okay, I'm not doubting it per se.
Okay.
But when I put my knowledge into it, it's 1 over 3x plus 10, which is
Okay.
mx plus
Plus c. So, okay, I think those are correct reasons to say it's linear. So we'll just put that there. And then x squared over 3, what type of function would you say that is?
I don't want the square to fool me, but I think it's an exponential function.
Exponential.
I don't know. I think so.
What about, remember with exponential, it's a base that is a numeric and then it's raised to a power. That's what
The
exponential.
base is raised to a power.
Yes, the base is raised to an unknown power, but the base is a number, like a natural number.
Okay. So could it be a quadratic? I think it,
What would make it quadratic?
I don't know.
What about, what's the standard form for a quadratic equation?
A squared plus bx squared plus
It's ax squared plus bx plus c, yeah.
AX,
So doesn't that look a little bit like this one? Like the x squared over 3.
It looks like the bx squared.
Like ax squared plus bx plus c. Okay.
It looks like the ax squared.
The ax squared part, right?
Yes.
Okay. Maybe we can go with that because
Quadratic.
for quadratic. Because remember, it cannot be exponential because that which is raised to a power is an unknown. But exponential, it's the other way around. That which is raised to a power is a number that you can say that's 2, that's 3, etc. Okay, so we're gonna go with ax squared plus bx plus c,
Which is a quadratic.
which is quadratic. Then what's y equals 10 to the power x?
Can I use the exponential?
Yes, you can. Yes, you can. And what about 1 over 3 to the power x?
I also think it's an exponential because it's raised to an unknown power.
Yes, exponential. Alright. Okay, so if we were to write these functions as inverses, the first thing we do is to swap x and y, right?
Yes.
So for the linear equation, when we swap x and y, what do we get?
X is equals to y over 3 plus 10.
Plus 10, okay. And then the second step we do is make y subject of formula, right?
Yes.
So how do we do that for this one? It becomes
Negative inverse,
okay, so it's
x
x minus 10.
and then we divide by 3 over 1.
Multiply.
Multiplication by 3 over 1. Which is that.
This 3x minus 30. something like that, okay? And then for the quadratic,
it's going to be x is equals to y squared over 3.
x equals y squared over 3. Then when we make y subject of formula,
Then you multiply by 3.
okay, so it's 3x equals y squared.
We plus minus root of 3x.
Like that.
Yeah.
Alright.
Okay.
Then for y equals 10x, we'll have x equals 10 to the power y, right?
Yes.
Then if we make y the subject of the formula,
that's where logarithm comes in.
yes, so log to base 10 of x equals y.
Yeah, we're making y the subject of the formula. Yes. To form a log in order to get an exponent or something like that.
Yes. Log to base b. So then here will also be x equals 1 over 3 to power y, and making y subject of formula, y equals log to base 1 over 3 of x. Alright. Alright, so to determine so we use the log to, I guess, come up with a way to express the exponential function. So log used to express inverse of exponential function. Exponential function. Alright. And so in other words, if x equals b to power n, or rather let me say b to power y, then y equals log x to base b, and b is not equal to 1, b is greater than 0, and x is also positive, greater than 0. What do you think happens if x equals 0?
Doesn't it become an error?
It becomes an error because you can't have a number raised to a certain positive number and then have x equals 0. Doesn't.
0 to the power of what?
Yeah, exactly. You can't have.
Make sense.
Yeah, you can't raise a number to a certain power and the answer gives you 0. And then what happens when b equals 1? When our base equals 1?
Won't the outcomes remain the same?
Yeah, you just get 1.
You just get 1.
So you just get 1. So the base of 1 doesn't really help us work with these kinds of problems. And what about x? Why must x always be greater than 0?
Because if it's 0, you're going to get an answer of 0 in And if you multiply a certain number with 0, it gives you 0.
Wait, say that again. I want to make sure I understood you.
I was saying, well, if you multiply any number with 0, it gives you 0. Any
Okay.
number raised to the power of 0 is 1, so it's quite pointless having a 0 there.
For x equals 0. So in other words, you're saying if I multiply x by itself, I get the same number, and if I raise it to the power 0, did I capture you correctly?
I get a 0 multiplied by 0 is 0.
Oh, okay.
Yeah. And then 0 to the power, okay, any number, 0 to the power of 1 still gives you 0. Or it doesn't give you 1.
It's any number to the power 0 gives you 1, and any number to the power 1 gives you itself.
So you see, it's still quite pointless. Unless I'm not understanding the question properly.
So my question is, let's say you have x equals b raised to power y. Why is it that x cannot equal 0? Or did I ask that before? Yeah, I want to understand. I want to find out from you why you think we can't have x equals 0. We can only have it more than 0, like 1 or 3 or 10,000 or whatever.
Doesn't it quite beat the purpose of solving for x?
I guess. So I want you to think about something like this, man. I agree we said if b is 0, we can't have that because how can I raise some number? I mean, how can I raise 0 to any power and get a different number than 0? Yes, I think that's why. And then I think in the second one, the other way to think about x being positive is that you can't raise any number to the power of a certain number and get a net result of 0. Yeah, so this one says you can't any number oh no. So this one of b being greater than 0 just simply tells us that 0 can't be raised to any number and give anything other than 0. And this second one tells us that you cannot raise a number, cannot be raised to any power and to a positive integer. Let me not say any power. To a positive integer power, and the answer is 0. Yeah, so let's see, let's say x is 0 No, x can't be 0. So I can raise, even if I raise 2 to the power 0, I still get 1. So yeah, so to any number, I cannot raise any number to any integer power and the answer is 0. At the very least, even if I substitute that exponent as 0, I'll get 1.
Isn't that what I said?
Yes. And then, so this one tells us that b is positive or greater than 0, tells us that 0 cannot be raised to any number and give anything other than 0. And then the second one simply says a number can't be raised to any number and the answer is 0. Okay. You want to refresh that? Oh, okay. Awesome. Okay. So let's discuss the following. We have P for Mr. P equals a raised to power n. And what is its inverse?
Inverse is p is equals to log a n. Log base n. Base a.
Log
n.
base a of n equals p.
Yeah.
Okay. And it looks so trippy now. Log to base b equals x. Shouldn't it be the power No. Let's discuss if this is true. Yeah. I don't agree with this. Our task is,
Find the truth.
is it true or false? Is it correct or incorrect? So we'll make it like a game. So there's a column for correct. There's a column for incorrect. Right. And then our first function is p equals a to power n, and we're told that its log is log p to base a, or rather log n to base a equals p. Now, is this correct or incorrect, that log, that inverse?
I wanna try this.
Want to try that?
No, like the way they are doing it. I've never tried it before.
Oh, as if you're proving it.
No.
Yeah, as if you're proving it.
Something like that.
Okay. So then are you doing the first one or the second one?
Is this one?
Yes.
This
Or
one.
you want to prove whether or not p equals log to base a of n is true or not using that method.
Something like that.
Okay, that's cool. Carry on.
That's wrong.
So the p equals log n to base a is incorrect, ne? So this means it's incorrect. Then what's the correct version?
N is equals to log base a p
Equals n. Great. Then the second one is y equals 2 to the x, y equals 2 to power x, and we're told that it's a one-to-one function, therefore one-to-one, therefore y equals log x base 2 is also a one-to-one function. How do we tell if a function is one-to-one or not?
If it has one x value corresponding to one y value.
Okay. Can we use the vertical line test to determine if a function is one-to-one?
Yes.
Will that work?
No, we can't use it. Maybe the horizontal. That'll work.
But we don't have horizontal line
We
test,
do.
Where do we have it?
Last year we had to do like the horizontal.
Does it?
Yes.
Okay, that's cool.
And like to test if it's like a function, if it was like parabola, if it cuts it twice, and then therefore it's a parabola or hyperbola or whatever the bola is. Yeah, so we just use that to test.
Okay.
So I think we can use the horizontal line test to test if it's a right.
Okay. Maybe I'll learn something from you as well. So, okay, you said one-to-one for log x to base 2. Let's see. I think y equals log x base 2 is also one-to-one function.
Why?
Because it looks like because I think if I remember correctly, an inverse is usually mirrored around the line y equals x, right? So if an exponential function looks like that, what would its inverse look like? It would probably look something like that. At least that's my guess for now.
That makes sense if you're putting it in the graph.
No graph form.
It makes sense for it to be like that.
Okay.
That's in my opinion, all exponential graphs and its inverses are one-to-one. Kind of makes sense for them to be like
that. Yes. It does make sense for a graph and its inverse to be one-to-one. You can also think of it from, remember the other class we did, what's that? Where if your inverse is a parabolic curve, instead of doing the two halves, you only focus on the one, so that your function is...
Yeah, you're limiting it.
Yes, to where it's actually a function. Okay, so let's check. Is it correct that for y equals 2 to power x, then the inverse is y equals log x base 2, and is also y one-to-one function? Is that correct?
It looks correct.
It looks correct. Let's investigate. So to investigate, we start with swap x and y, make y subject of formula, what did you get?
That.
Alright. So I was just making yeah, okay. So this one, it is correct. So just just write it here. Correct. And it's log x equals y. That's great. Then the third function is what? X equals.
Back into exponential.
Oh, moving it back. Alright. Log y to base 5. And this is the inverse of 5 to the power x equals y. So let's first test. If we have what's this? 5 to the power x equals y, then log of x to base 5 equals y. Is that correct? Is that the correct way to do it?
I know we're trying to find if this is true or not.
Yes, I get we want to prove if x equals log y base 5 is the inverse of y equals 5 to the x. So we want to prove whether or not that's true. We'll have to find the inverse of y equals 5 to the power x. And how do we do that? Swap x and y. So x equals 5 to the power y. Then write the inverse. So it'd be log x to base 5 equals y. Is that what you got?
Yeah.
So that means x equals is not correct, ne?
Round.
So this is incorrect. Correct form is log x base 5 equals y. Alright. Then the last one, k equals b to the power t. K equals b to the power t. And we must prove whether or not t equals log of k to base b is its inverse. So how do we find the inverse? We swap x and y. So we'll have t equals b to power k. Then we make k subject of formula. That is k equals log of t to base b. So that makes that one incorrect?
Wrong.
Incorrect. the correct form is k equals log t base b. All right.
So the first one is correct.
The first one is correct.
It is correct.
Why?
I did it again. So do it.
Okay, let's do it. It's p equals a to power n. Swap x and y, so n equals p to a to power p, correct? Then we make p the subject of the formula. So then it becomes p equals log n base a. So it is correct. Well done for spotting that.
Thank you. I saw something was up here. But it's n cannot be the subject of the formula because it is an x.
Okay.
Yeah. So it is an x value. So it cannot really be the subject of the formula because we're trying to make y the subject of the formula.
Okay. That makes sense. I think we should check all of our answers there, just to be sure. So this is correct. Yeah, this is correct. Log n base a equals p. And the second one, is it correct?
The second one.
Yeah, we're checking all of them.
Which one is the y is equals to 2x? I believe it's correct. I believe it's correct.
Let's just check it again.
Double check, you don't trust.
Yes.
I think I made a mistake somewhere here. When I said I was trying to use this formula. So I stopped using the formula, I just used the basic. Because this is wrong for no reason. So yeah.
Okay.
This is unnecessary.
I'll show you how we can apply that just now.
Okay. But still it's unnecessary for swapping x.
I'd like to think so too, but I think there's also some use for it,
Yeah.
just to illustrate this concept as well. Log n base a equals p. Swap y and x, so x equals 5 to power y, and take the log x base 5 equals y, and swap t and k. Take the log, so log and it becomes log what? Base b equals k. Hold up. Oh, okay. So Oh yeah, so the last two are incorrect and the first two are correct. Yeah. No, our answers were correct. It's just the first one that was off.
Wait, I don't understand.
No,
Oh,
I
the
was saying-
answers here were saying it's incorrect.
Yes,
The
I was
answer
saying
is incorrect.
incorrect. Yes, that's
Okay.
what I'm saying.
So the first one is the one that like
We
phazamiseka.
botched, yeah.
Okay.
Alright, so we were using. You said you wanted to prove that. What was the first problem again? It's p equals a to the n, and we wanted to prove that its inverse is log n base a of p, right? Alright, so what does the proof say? It says we take log on both sides. So log p is log a to power n, isn't it?
Yes.
And then
Then the y jumps
oh yeah,
down, the
it
exponent
becomes a
jumps
coefficient.
down. Yes.
So log a equals log p, right?
A.
Mm.
Yes. Yes.
Then I can divide both sides by log a, so that n equals log p over log a, and log p base a.
Let me just say, what happened to the other log? Does it divide? What happens actually? What's the process behind it? Yeah. Do they add? Do they like what?
We need to visit the rules of logarithms just so we can be able to answer that question. Alright, so it's this one here, log number 4. So
It's just how it is basically. It's just how it
this
is.
how it
meant
is,
to
yeah.
be. Oh,
So this one are you okay, something is not adding up.
Something is not.
Something is not adding up because
Weren't we supposed to swap x and y?
wait.
But still.
Something
Yes,
is
we
not
were
adding
supposed to swap x and y at the beginning. Swap x and y. We swapped x and y. And that's why it doesn't make now it doesn't make sense. Yeah, we swapped it. I wanna say we swapped it like interchanged x and y. Here's my reason. It's just the
Okay.
base. It's just.
Let me start here. So maybe let me say swap x and y. So I have n equals a to power p. Then I can take logs on both sides. P log a and divide by log a. Equals p. Therefore p equals log into base a. Yeah, when you do swap x and y and then you follow that proof, you do get the correct answer.
Kind of makes sense now. I didn't swap x and y.
Yeah, that makes sense. So this here is correct. This here is correct. this one here is incorrect. Drama? No, why?
You don't have to make it that big.
Well, I mean,
I like being extra.
I like being extra.
Yes.
Yeah,
Okay,
extra.
so I can't find my eraser.
You can't find your razor.
No, when I took it out.
It fell
Really?
under this chair.
And I didn't see it.
You probably didn't hear it either.
Found it.
You found it.
So, side note, swap X and Y.
Yeah, always.
I don't know why I didn't pick that up at the beginning.
So swap X and Y first. Then 2 make Y subject of formula. Alright. Subject of formula. Then we've got worked examples. Let's do those. So worked example. Alright, so we're given 5 squared equals 25. And we must write the following exponential expressions in logarithmic form and express each in words.
Wait,
In words, yeah.
I didn't know it. Like, okay. What do they mean in words? Like in a sentence?
Like as if you would explain it to someone, yeah, in a sentence. So first we must write the logarithmic expression. Let's start there. Let's start with explaining them as logarithm, or rather writing them down as logarithmic expressions. So what we'll do is we'll say
I wish you would swap X and Y. So it's 5 to the power of 21 as equals to 2.
Let's start with that proof you just did now. Take logs on both sides. So
Yeah, don't forget to swap first. You swap first before putting logs on both sides.
really?
Yeah, look. You swap first. So there's no expression that comes like this currently.
I just want to see something. 2 equals log 25 over log 5, which is 2 log 25 base 5. Okay. It says 2 is the power to which 5 must be raised to give the number 25.
So it doesn't work the same.
Okay, I'll tell you why here. You have to swap X and Y. Remember, we do the swapping X and Y when we are finding the inverse of a function.
An inverse of exponential is log.
Yes, but where we start when finding the inverse of any function, we first swap the X and the Y. Then after swapping the X and the Y, we then make the Y in the swapped equation the subject of the formula.
Okay.
So with exponents, that's when you apply the logarithmic function when you're making y the subject of formula. But before you do that, you have to change the first equation or expression to swap the x and y. Let's start here. So let me clear the frame. Let's start here, né? Okay, so if we have a function y equals a to power x, right? We don't apply log here. So we don't apply log just yet. Don't apply log just yet. Apply log. So we first start by doing swapping x and y. First swap x and y such that x equals a to power y. Then apply log. So when we apply log, then we'll have log x equals y log a, and y then becomes log x over log a, which is log to base a of x. Yeah, so you are correct. We do have to apply swapping x and y, but first we look at our expression, and if it's given in the form y equals something to power x, then we must find the inverse. Then we start by swapping x and y. For this type of problem though, we're not necessarily looking for a function like 5 squared equals 25. We're not looking for a function, so we don't have to swap anything there. We can just work directly with it. So we can say log, or twice log 5 equals log 25, and therefore 2 equals log 25 over log 5, which is log 25 to base 5. So this one we can directly solve to make like this, and in words we'll have to say 2 is the power to which 5 must be raised to give the number 25. So this is a power. Power to which the base 5 must be raised. So 2 is the power, the base must be raised to give 25. So our base 5 must be raised to the power 2 Alright, so 2 is that power, right? To which base 5 must be raised to give 25. And that simply means so this is an inverted way of writing this here, right? And that simply means 2 is the power to which the base 5 must be raised to give 25. That's the logarithmic expression verbally. Alright. So it's like saying Joy eats her muffins versus the muffins are eaten by Joy. Or Joy's muffins are eaten by her.
Okay.
Yeah, it's kind of like thinking about it like that. So 5 squared, or 5 to power 2 equals 25 would be the same as 2 is the power to which base 5 must be raised to give 25. Yeah, it's like the other one goes at it in reverse.
Like 5 to the power 2 equals 25.
Yeah, 5 to power 2 equals 25. But in log form would be 2 is the power to which base 5 must be raised to give 25. We can do the other one. It says 10 to the power negative 3 equals 0.001. And if we just apply logs, then negative 3 log 10 equals log 0.001. Negative 3 equals log 0.001 over log 10, and that's to base 10 of 0.001 is negative 3. Therefore, negative 3 is the power to which base 10 must be raised to give 0.001. Alright. And I guess with the other ones it's the same as well. Let's do so, but that confusion I say I get the one of saying, yeah, so only when we're looking for the inverse, we start with the original equation, swap the x and y, and then follow the procedure of making y subject of formula. But after we've swapped the x and y, but it doesn't mean if you're given a numeric problem, you have to swap, because there's no x and y to swap really there. Yeah. Alright, so we can do I don't want us to spend time. Oh yeah, let's do these ones here. You can do D, you can do F, you can do D all the way to H. Let's do those. So exercise 2.6. Exercise 2.6, number D. It's y equals 2 to the power x. We must find the inverse, right? Write the following in logarithmic form. So this would be x equals 2 to the power y. Then taking logs, we'll have log x equals y log 2. Therefore, log x to base 2 equals y. E would be q equals 4 to power 5. Okay. I actually would love to test my theory now. Have you written number E down?
Yep.
Oh, okay. I want to check. Okay, let me first calculate it.
You want to check the answer?
Yeah, I want to see if following the procedure that I just said is the procedure is indeed correct. For the power Q, log 5 equals Q log 4. Q is going to equal log 5 base 4.
2.6.
Is 2.6.
D, right?
D and then E.
Looking for E. Should I tell you the answer? So what's your answer?
My answer was, for D, it's y equals log x base 2.
For E?
For E, it's q equals log 5 base 4.
Wrong.
It's log
Q base 4 is equals to 5.
log q. So it's like just log q equals 5 log 4. Then 5 equals log q over log 4. 5 is log q base 4, like that.
Yeah, like that.
Okay. Then something is not. Because now. Okay, keep on that page, ne? I want to see something. See 4 equals y to power g. Yeah, y equals 4 to power g. So let's say we've got 4 equals y to power g. So if we just take logs directly, equals g log y. G equals log 4 base y. Then what's the answer to number F?
Log 4 base y is equals to q.
Okay. This is f, man. Then what equals let's say number g, 9 equals x minus 4 to power p for Mr. P. Alright. So if I just say log 9 equals p log of x minus 4.
Yes, I hear you swapped
For this one, f
for e.
for e, I swapped here. Okay,
Q
let me.
and 5.
Yes, q and 5. I swapped initially. This is the first part where I swapped.
Shouldn't have swapped.
Shouldn't have, yeah.
But how do I know when to swap and when to not swap?
That's what I want to uncover as well.
Because yes, don't swap, but when is the right time to not swap?
See, that's why I don't like making general remarks to say you can just do this, because you might not get away with it all the time.
Sure.
But there has to be a sure way of saying, I can test this way and I will get a correct answer. But that's usually by following the correct procedure, and usually the correct procedure is, am I also using the correct words? Yeah, so it's not that easy for me to say, yeah, you can just do it. Like, no, it's not that straightforward. But anyway, this will equal log 9 base x minus 4. Then what's the answer to number g?
Log 9 to the base of x minus 4 is equals to p.
Okay, so this type of exercise is simply testing whether or not you can apply a log on something that has the form y equals a base to power x. Okay. So here our goal, can log be correctly applied to y equals b to x? That's what we want to check with this exercise. I believe only when it says okay, maybe let me just say but if you want to test when you can apply the swapping of x and y values, I think that's when you have to now discuss the properties of the inverse. And the inverse would definitely not be the same as the original function. So log is a way to express an exponential function's inverse, but the inverse of an exponential function you get by first swapping x and y values and then applying log. So like I said before, first swap x and y and then apply log. Okay, so log cannot be negative or cannot be equal to 1, or must be a positive and cannot be equal to 1. That's the base of it. The value of the base infinity.
So you mean which is never on time?
Yeah, it's like a half an hour early or something.
No, we're doing at 33 minutes past 33. It's
Yeah.
like 27 minutes to 2 or something like that. 27 minutes to something. And now
Yes.
it's like a minute late. I see you try to fix it, but it's still a minute late. It's actually 2 minutes late.
Later than we normally go straight with.
Yeah.
It's a minute earlier.
What time is it now?
It's 14. It's 1:32.
So it always use at 1:32.
Something like that, yeah. Okay. So I want to give the correct advice. And the correct advice would be, for me too, would be, only apply the log if you're given a function first and then they say find its inverse. Then you swap the x and y and then you do the inverse.
So I only apply the log and swap x and y only when they tell me to find the inverse.
Find the inverse, yes. But if they say write the logarithmic of this, I think you can get away with that. I'd like to think that that is 100% correct. Because I don't want to misguide you and give you comfort answers. Then
I'll just see with the practice examination papers and
yeah.
see how it is along.
Because even if we look at worked example, exponential form to logarithmic form, when they just say write the following exponential expressions in logarithmic form, none of that says write an inverse. Yeah. So you can directly just apply the log.
Yeah, but look, in the activity, right, in the exercise, there were parts where we had to, do we have to
swap x and y?
Did we?
Look, for example, that investigation we did here with p equals a to power n, right? We had to prove if that answer they gave us, p equals log n base a, we had to prove if that is the inverse of p equals. So we have to then apply the swap x and y, then apply the inverse thing. So here, let me just revert back to here. So like in this part of the handwritten note, yes, it is true. So if we're given this, and then they say find inverse, right? Then they say find inverse. Then we don't apply log at this stage yet. We don't. We apply log after swapping x and y. Yeah, I think that's the safest I can say. But if you find anything that says no, Mr. P, you're not correct, by all means, let me know so I can acknowledge it and then,
figure something out.
Yeah. But you see, like here, log is an inverse of an exponential function. But if you're given a function of an exponential expression, function being y equals a to power x, but an expression being like 5 squared equals 25, that's an expression. But if it were 5 to power x equals y, that is a function. That is a function. So if that is a function, then with a function, the inverse, we do the swap x and y and then apply the log rules. Yeah, I think we can end here. So I just want to write that down. Okay, so I think we should make different we should differentiate rather exponential function versus exponential expression. Alright, so with a function you have y equals a to power x, and with an exponential expression you can have 5 squared equals 25. Now if you want to write the inverse here is just direct. So you can say log of 5 squared equals log 25. 2 log 5 equals log 25. Therefore 2 is the power to which base 5 must be raised to give you 25. And then here, for a function, the inverse starts off as x equals a to power y. Then you take logs. Therefore, log x equals y log a, and y is log x base a. Because when you look at it this way and that way, it kind of looks like, here you just apply directly. Here you have to first manipulate and then apply. Yeah, I understand where the confusion can come.